Hello, good morning, good afternoon, or good evening, depending on when you're watching this. And thank you for joining us in yet another video in our ecology series of, well, information. Today, what we're going to be discussing is population ecology and how populations can grow over time, as well as what can limit their size and kind of keep everything in check. So as we go ahead and progress through this, keep track of any questions you have, and make sure to go ahead and bring them up to your teacher. Let's get started. The first thing we need to talk about is what can influence population size. Factors that can affect a population size include birth rate. So the more individuals being born, the larger the population. The mortality or fatality rate, the death rate. The more organisms that are dying, the smaller the population is. So that will decrease the numbers. We have immigration, that is organisms coming into an area. That will increase the population size. So immigration, population size goes up. Meanwhile, emigration means organisms are leaving the area. So if organisms are leaving the area, that means that decreases the population size. So immigration in, emigration out. Biotic potential. What biotic potential equals here is the reproductive capabilities or potential of an organism. That is the rate at which a population could grow if it had unlimited resources. So if a population reaches this biotic potential, it would have what we call exponential growth. So for example, if you go ahead and look at the population size over time, if organisms didn't have to worry about resources, their population size would gradually start to increase. Now this is something that's actually affecting humans as a species. Over time, we have found more ways to go ahead and gather our resources that we need. So as such, the population size over time has increased drastically. Another example of this would be the J-curve or exponential growth of flies if over time they had unlimited resources. So as you can see here, we start off at the bottom in the lower left-hand corner here. So as more flies go ahead and begin to be produced here, they begin to mate, have more and more and more, and over time, the more flies that are available, the more that will eventually go ahead and reproduce, produce offspring, and the trend will continue. So this is what we call the J-curve. The J-curve represents exponential or unlimited growth, like a rocket to the moon. Called the J-curve because, well, it looks like a J. However, in most cases, things follow the S-curve, also known as the logistic growth curve. This graph shows a typical population growth curve. So there is a slow increase followed by rapid growth. So if you look in the bottom left, you'll see that things start off relatively low and seem to keep that way until they get about to the halfway point where things go ahead and increase exponentially to a point. As you can see, it does eventually go ahead and level off. And where it starts to level off is when the population size gets to something called the carrying capacity. The carrying capacity is the total amount of organisms a population can go ahead and, an environment can go ahead and support without severely negative consequences. So carrying capacity is the total number of organisms an environment can hold without consequences. So the way I want to describe this is, let's give you another example. Think of an elevator. So an elevator has a maximum amount of occupants or weight that it can hold. So if you go ahead and stay under that weight limit, things are just fine. But the moment you go ahead and go above that weight limit, you run the risk of things going ahead and going south, both metaphorically and literally. So what we have there is if you go ahead and exceed that carrying capacity of this elevator, you exceed the maximum number of people in there, the elevator could drop, causing a drastic decrease in the number of individuals present. The same thing happens if organisms go past the carrying capacity. So the carrying capacity, if it is exceeded, organisms can continue past that for a bit, but once they get too far past it, their population size will begin to drop rapidly. And in some cases, potentially unrecoverably. Now, things that go ahead and influence the carrying capacity are called limiting factors. We'll be talking about those here in a bit. First, we need to go ahead and briefly discuss population density. So simply put, population density is the number of organisms in a given area. As you can see here, the photo on the left is a bit more dense than the photo on the right. So the more organisms that come into an area, the larger or greater the population density. Now, like we said before, there are things called limiting factors. Limiting factors are any factor that can control or limit a population size. And we have two different types. The first being density dependent. So these are normally biotic, and if you remember biotic, we're talking living factors. These things include disease, food, parasitism, predation, and competition. So these factors are going to have a much higher impact on the population if there's more individuals there. So think about it. The more people there, the more likely disease is to spread because people are coming in contact with each other much more frequently. The less amount of food they'll have because there are more mouths to feed. Parasitism, same thing. Parasites will be able to spread more easily. Think like the bubonic plague back in the day. Predation and competition. So the more mouths there are to feed, the more competition there will be. Now on the other side, we have the density independent factors. These are the abiotic factors. These are going to have an impact regardless of how large the population size is. And these include things like temperature, storms, floods, drought, as well as habitat disruption and natural disasters. So these are going to have an influence on the population size regardless of how many people are there. For example, not many people live in the frigid Arctic and Antarctic temperatures of the top and the bottom of the globe. That would be a great example of a density-independent factor that limits the population size just by being cold. Now here's a great example of a density-dependent factor being implemented. Here we have two separate species of paramecium. So these paramecium, if left alone, so if either species was cultured by itself, follows that logistic growth curve. It goes ahead, increases, and then once it hits the carrying capacity, it tends to level off. And that is represented by the dotted red line here. However, if you put both of them in the same area, what you're noticing is that the Paramecium aurelia, the black line, and the Paramecium caudatum, if cultured together, is a bit different. The Paramecium aurelia follows the logistic growth curve, where it increases slowly and begins to level off once it hits its carrying capacity. But the Paramecia caudatum, on the other hand, increases and then dramatically starts to decrease over time. What's going on here is it is being outcompeted. It is being outhunted. The Paramecium aurelia is much better at going ahead and hunting and eating the food in the area. Meanwhile, the caudatum, since it can't go ahead and compete, the numbers are starting to die off because they can't get enough food. So here's a great example of density dependent. This would be competition. This also represents the competitive exclusion principle, where we said that two organisms in the same area can't occupy the same niche without something like this occurring. The last example I wanted to go ahead and talk to you about is a density-independent example. So here, we're talking about a series of floods that went ahead and affected the population sizes of finches on one of Darwin's islands. So as we can see here, in about, I'd say that is 1975, a little bit before that, the population size of finches on this island was about 1,400 birds. So once that happened, the flood occurred between 1975 and continued until 1978. So as we see here, the number of birds is drastically dropping. And even though the drought ended in 1978, it was too much and the birds couldn't recover. So this was an example of an abiotic factor, drought, going ahead and influencing the number of organisms that live in an area, affecting the number of finches there, as well as the food that was available, which causes the size of the population to decrease. So, ladies and gentlemen, this gives you a brief introduction to population size, as well as the factors such as limiting factors, carrying capacity, and others that influence how many individuals can be in an area at a given time. If you have any questions, please feel free to go ahead and ask your teacher. Thank you for joining us for another lesson. Until the next video, you all take care of yourselves. I'll see you next time.